so that I introduce you. Perfect. So thank you everyone for joining us again on this Ghana Numerical Analysis online seminar series. And today I'm very, very happy. We have Professor Jaouad Danane from Morocco, who is going to talk to us on mathematical and numerical analysis of the stochastic epidemiological models. And as I said to him earlier on, this is an area that I barely see this kind of research also in Ghana. And I'm hoping that the knowledge he will share with us here will kind of help us understand the ingredients and the tools that are needed to do this kind of research. And then hopefully going forward, we can also have some Ghanaian researchers or researchers in Ghana who will be willing to do this kind of research as well, collaborate with him, and as well as share the knowledge as well. So thank you, Professor Danane, for joining us, and you are welcome to continue your talk.
Thank you, my friend Stephen, and thank you very much of the presence of the PhD student and my colleague in the. So my topic talk is about the stochastic and numerical analysis of the stochastic epidemiological model. This topic is try a collaboration between three major topic. It's the mathematical topic given by the mathematical stochastic and the computer sciences given by the numerical analysis and the numerical simulation, and the third topic is about the epidemiological models. More precisely, it's the infectious disease. Now, so for this, I prepared the plan of my talk. It's in the first time we will give an introduction, and in the second time we will give some motivation of the mathematical modeling in the infection disease. And we try in the first time, first work, it's about the stochastic model of the COVID-19. Then we will try the interaction between the individual's population. And in the second time, we will give a stochastic SECV. So it's meaning the susceptible, infected, chronic, and vaccination. And here we will try the vaccination and the program of vaccination, or the strategy of vaccination is dedicated to the infected and the chronic population. And in the end of this talk, we will give some stochastic viral infection model. When we will try the viral infection model, that's mean the interaction between cells and virus, and we introduce the immune system in our study. So it's very we will be try a very nice result in this parts. We will give a mathematical models. In the second part, we will give the mathematical analysis, and we will try to case is the extinction of the infection and the persistence of the infection, and finally we give some numerical analysis. So it's very nice to start by the definition of the infection disease. When we say the infection disease is a disease caused by the transmission of a microorganism such as the virus, the bacteria, and the parasite, and some as the fungus, For example, or an example of the infectious disease, we have the malaria, the human immunodeficiency virus, the hepatitis B virus, or the hepatitis C virus, and more recently we can try also the COVID-19. So about the infectious disease in Schaefer are responsible for 17.7 million of deaths per year, which represented one third of the mortality. So this disease represents a major global public health. So the importance, the question here, how can controlling this spread? If we have a positive infected by the antivirus, how can controlling the spread of the infection? So the mathematical tools given some tools to controlling and to study the spread of the infection in order to research the strategy of the vaccination, of the controlling, of the treatment, of the isolation and so in the last recent years, we can remark that the mathematical modeling of infectious disease be an attractive phenomena of many research. For example, the modeling of the hepatitis C virus, the hepatitis B virus, and the human immunodeficiency virus. And more recently, we can give the result of the modeling of the COVID-19 is a newly detected, such as a pandemic disease that is responsible on a great epidemic disaster. This virus has known several changes at the level which give several variants such as Delta, VOC 2020, and other variants of this virus. So the question, how to modeling? If I research in the mathematical modeling, I want to try the modeling in the infectious disease. We have in the general the policy advice. And the policy advice, we adapt this policy advice to give the policy question, and the policy question we build in this policy question to give or to illustrate the available data. And in the when we have the available data, we try the available data, we can give some scientific understanding on the infection, and we give some scientific insight or some scientific recommendation, and we collect a new data collection. And this process, we can help a mathematical or a mathematical begin on the modeling of the infectious disease to try the infectious disease. But if we have a report, we have a data, how can try this data? Or the basic data, we can find the basic data in the filed reports or the clinical study or the laboratory experiment. After this step, we can research the distribution of the input parameters. Is a constant, has a probability distribution or a normally distribution, or is a constant. If we try the different distribution of the input parameters, we can now illustrate the model. When we illustrate the model, we give the projection. So the projection give in this case, we have the disease burden or the outbreak trajectory or the cast of this infection. So now we research the strategy or the policy is the strategy of the vaccination, of the control, of the quarantine, or the sensitivity. And we go now in the model and the boarding or the running this model and to give a new result and to continuous in this cycle, we can try or controlling the spread of the infection. Now, how to modeling? If we have the data, if we have the distribution of the model, how to modeling the infectious disease is one of the major questions. So we have a case we can use the deterministic model. We by using the ordinary differential equation. So it's be a classical model of the ordinary differential equation. One can take the memory of the infection by introduced by the fractional derivative. And now we will try the fractional differential equation. So in order to take the memory of the infection, or we can try the stochastic model by using the random noise or the Levitt jump, or both the random noise and the Levitt jump. Random noise is when we have the perturbation is almost sure converge to normally low. But the Levitt jump is a process or when used when we want to modeling the event inattentive. So, for example, the trembling of the root, or for example, if we have the discontinuity of the infection, and more other example of this parts. So the first mathematical model of the infection is illustrated by the Kermack and McKendrick in the 1927. Is represented the interaction between susceptible, infected, and recovered population is SER model. This model where beta is represented the route of the transmission of the infection, and the alpha is the route of the recovered population. This model have be an exponential form or change, because we have changed this model by changing this function, because this model give a interesting result when the population we have a small population. But if we have a large population, this model not works, and we can change the infection function by a saturated route or other function. We don't try here the recruitment routes by introducing. We can introduce the natural the exponential the exponential route of growth route, or we can try the case of the logistic growth route, and we have more motivation, and we can introduce added other class, such as the class of exposed individual, or the treatment, or the vaccination, and other more class. So now if we have the classical it's in this talk, we want to try the case of the stochastic the stochastic model. Now we can give the definition of the stochastic model. The stochastic model is equation. It's the equation, the variation of the U given is equal I2 U T dt is the continuous or the deterministic part, and the stochastic part, it's the part in the red colors. So the B of TUT, the WT is this part is B is the part ported by the Brownian motion, and the second part is the discontinuity of the processes of the modeling is given by H of XS. So if we have any function defined on the parameters we can by using the auto formula we can try or find the derivative of this function is given by the following definition. By LF is the part of the deterministic, and the dw is the part of the Brownian motion, and the tilde n dx ds is the part of the Levy jump. With the derivative or the LF is given by the following expression. So we have illustrate the crucial tools in the mathematics calculus of the derivative of any function of any parameters of a stochastic model. So our first model is a model illustrates in collaboration with the Professor Karamelleli of the University Hassan II of Casablanca, and the Professor Zaki Hamouche of the University Moulay Ismail, Morocco, and Sopi Nizar of Saudi Arabia. This result is published in the journal Result in Physics, and this result represent the interaction between the susceptible is represented by S, and EU represented the infected population, and Q is the is the isolated population, and R is the recovered. With lambda is the growth rate of the population, zeta is the mortality of the population, and beta is the it's the root of infection, and eta is the root of date, or the date of the infected population due to the infection, and kappa is kappa is the root of the recovered, and D is the root, the date root due to the infection in the isolated population. With sigma 1, sigma 2, sigma 3, sigma 4 is the volatility of the due to the Brownian motion, and Q1, Q2, Q3, Q4 is the jumping process due to the population respectively as U, Q, and F. So this model, because it's a stochastic model, and it's a epidemiological model, the population of or the solution of our model will be exist and will be positive of the positiveness of our solution. And in order to try, we have the following result of an initial conditional in R plus power 4. The model 2 has a unique global solution defined by in the positive part of the R power 4 almost surely. Here we have defined a function of Lyapunov, and we give we give a characterization or by using the Ito formulas. We have proof that that's the expansive or the time will be infinity. So now we can try the mathematical analysis of this model. In order to give the mathematical analysis of this model, we can, in the first time, to calculate the reproduction number of the deterministic version of the model, or by ignoring the stochastic parts. The R0 is equal, as given by this form, by using the next matrix generation, and we can try that we can calculate the reproduction number, and also we can find the steady state of our model is given by the free infection equilibrium, where is epsilon f is that's main when the susceptible population is in the range is maximum is lambda divided by zeta, and all the rest of the population is equal 0, and epsilon stars is equal star A star, and Q star R star is given by the following expression. So now we can try, because here our object, our subject here in this paper, it's to characterize the solution around the free equilibrium and the endemic equilibrium. What's the comportment, what's the behavior of the infection around the endemic if we have R0 is less than 1, and if R0 is bigger than 1, what's the behavior of the infection around this equilibrium. Now we have the following results. So if we have L1, L2, L3, L4 is positive, and R0 is less than 1, that's implied that the limit set of 1 divided by t, the esperance of 0 and t of s eta lambda divided by zeta pow 2 plus u2 u pow 2 and q pow 2 plus r and pow 2, the eta is less than m1 divided by rho1, with M1 is given and rho1 is the mean of L1, L2, L3, L4. That's it's what's the biological meaning of this result? This result means that that we have the fluctuation of the solution around the infection. That's mean we can control of the regions of the infection, and or the converge. If we want to converge around to the infection to the free infection equilibrium, we can illustrate the L1, L2, L3, and L4 is positive, and the R0 is less than 1. Now about the endemic equilibrium, so what the property of the solution around the endemic equilibrium. If we have R0 is bigger than 1, and L5, L6, L7, L8 is positive, and with 8 zeta minus D is positive, then we have the fluctuation of the solution around the S star, U star, Q star, and R star. So that's mean that's if we start around the endemic equilibrium, and if we have the conditional R0 bigger than 1 and L5 to L8 is positive, and with zeta minus D is positive, we can get that the solution have a fluctuation around the endemic equilibrium. So now about the approximation or the numerical simulation, we have the following equation. Dx is equal f of txt dt plus sigma of txt the wt plus part of the jumping. So now we can, the solution of our model, we can integrate the bout part of the equation 3. We can give that we have the solution is given by the following expression. So now in this we can modulate that the first part is the continuous part. We can approximate this part by the Milstein-Hager order method is given by the following expression. And the second part we will be try this second part in the next slide. So here the Milstein-Hager order method is given is xk plus 1 is equal xk plus f of tk xk times delta of t plus sigma of tk xk times wk plus 1 minus wk and plus 1 divided by 2 sigma power 2 tk xk times wk plus 1 minus wk power 2 minus tk plus 1 minus tk. That's mean exactly it will be replaced this part by delta t, and we can give the approximation of the continuous part. But about the second part, here we have two cases that try. If we have a jump, if we have no jump, and about this we consider any infinitesimal interval te plus 1 is a sub interval of tau e plus 1. There is no jumping, so that's meaning this part will be is equal as 0. If there exists is only one jump point tau e in this interval, so that's meaning that we can approximate to this part by g of tau e minus x tau e minus times q tau e zeta of tau. So we can now replace this part in the because this approximation is between te plus 1. Now in the interval 0 t we will be a sigma of or the sum of between e equals 0 to n of g tau e minus x tau e minus q tau e zeta of tau e. It's a nice approximation of our numerical solution. So the approximation of the x will be given by the following expression, and we can program this result in the MATLAB or in the Python or the Mathematica or the R logiciel, and we can give it or we can get the numerical simulation of the result. Here we can in the case when R0 is less than 1 and when L1, L2, L3, L4 is bigger than 0, so that's mean we have the conditional of the theorem of the solution or the propriety of the solution around the free equilibriums. We can remark that the deterministic is represented by the blue, and the red represented the case of the Levy noise, and we can remark that we have the fluctuation of the solution around the free equilibrium. The both result or the same result in the case or the propriety around the endemic infection, and we can give that we have the fluctuation of the solution around the S star and around the U star and the Q star and the R star. So these are very beautiful results. We have tried in this paper. We have tried the strategy of isolation and the impact or the influence of the strategy isolation or the isolation strategy on the population when we have the infection of the COVID-19. This result we can find the paper in the following in the journal Result in Physics. Is published in the 2021, and so it's the first part. We finished the first part of my talk, and the second part it's another stochastic SECV model when we represented the interaction between the susceptible, infected, and chronic and vaccinated population. So here we have introduced some new assumption. If we can try the vaccination or the program of vaccination of only the infected and the chronic population, and so we can remark here that rho 1 is represented the treatment or the vaccination of the population of the infected, and rho 2 is represented the vaccination due to the chronic population. And we can also remark here about the perturbation. Here we have the perturbation of the transmission function is beta ES. We will be replaced by the beta replaced by beta plus sigma plus the part of the jumping. So this paper is published in the 2022 in the journal Applied Sciences MDP with the collaboration of the Professor Srivastava is an editor in the Journal of Chaos, and also it's in the University of Canada. It's a nice result gated in this paper. So of our study, and we because we try a epidemiological model, the solution of our model will get in the set gamma. With the set gamma is given by the following expression: is the sum of all the population is belong to this interval and is a positive. So by giving some Lyapunov function and apply the Ito formulas, we can prove that we have the persistence of the infection. So here we about the extinction of the infection. We have tried the extinction of the infection. So the disease due out in the case where we have beta times lambda divided by me is less than O1 plus epsilon plus me plus sigma pau2 divided by 2 lambda pau2 divided by alpha plus me pau2. So if we have this conditional, that's meaning if we can control the volatility sigma, we can get we can get the extinction of the infections. That's meaning that the limit of UT is go to 0 when T go to plus infinity, almost surely. In order to prove this result, we have about the data of this proof. We can get the result in the journal Applied Sciences, and about this result we have illustrate incidence function, sorry, an Lyapunov function, and we try by using the Ito formulas, we can get this conditional, and when we have this conditional applied, that U2 is go to 0 when t go to plus infinity. So about the persistence of the infection, if we have now, we can control the volatility, but by another conditional. If we have this conditional is realized, we can prove that the persistence in mean of U and C and S and V, that's meaning the persistence of the infection. About the numerical simulation here, we can return in the previous part of the numerical simulation. Here we have tried or we have approximated this part by using the Meershtein-Hager order. In this paper, we have approximated this part by the range quota method, and we can, but not the classical range quota of the differential equation, but of a modified, because this is a continuous part. We can use the range quota method, ranking 4, and we give an approximation of this part. And about this part, we can use the same used in this approximation. So about the numerical simulation here, we can try about the result of the extinction if the conditional of the extinction is realized. So that's meaning we have the persistence of the susceptible and the infection due out. And about the case of the persistence of the global population, we can prove that we have the persistence also of the susceptible and the infected population, and the same behavior of the others population, the chronic and the vaccination subpopulation. Now, because we have the perturbation here, it's on the parameter beta, so we can give a comparison between different value of beta, and we can give a sensitivity of this parameter on the infection. So here we can remark that when beta is very small, or beta equals 0.5 and is represented the maximum of the susceptible, that's meaning we have minimize the number of the infection, and that's meaning our study is a very nice tools or to controlling the infection. So now we can go to because we have trying the stochastic in the population of the individual. Now we can try the infection on the viral infection model by using the stochastic. So modeling the viral infection has attracted the attention of the many authors in the recent years. If we have the transmission of any virus and the interaction with the cell, we can call this part it's the viral infection. So it's very nice to recall that the first simplest viral mathematics model is suggested by Novak et al. In the 1996, and this result has played a significant role in starting different viral dynamics research, because it's the starting point of the modeling in the viral infection. The mechondric antikeramac is represented the basic model of the when we try the population of the individuals, and when we try the population of the cell or the interaction between the viral load and the cells and the immune system, we can use the basic model is given by the Novak. And so it's about this model is represented the interaction between the susceptible cells or the healthy cells and the infected cells and the free virus. So our study is about to study a viral infection, but a more specially model is the model given by Jaouad and all. It's a paper published into 2002. And he represented the interaction between X, U, and Z, where here X and represented the uninfected cells or the healthy cells, and the second represented the viral load, and Z is the lytic and non-lytic immune response. Our study is our model is given by in the collaboration with the Professor Khadija Akhtim of the university and Monsieur Sir Adi Zitouni of the University Jaouad and the Professor Karam Allali of the University Hassan of Casablanca. In this model, we have perturbed the model of Jaouad by using the perturbation of the parameter beta by the sigma and a second part of the jumping. So this model, we have studied this model by given the existence of the solution of our model. If we have X, the condition, the initial data is in the set gamma, we can find that there exists a unique positive solution XTU to ZT in the set gamma, almost surely of this model 12. And with the parameter S is equal the mean of A and D. So about the classical about the classical result here, we can remarks that if R0 is less than 1, the infection-free equilibrium is globally stochastically asymptotically stable on gamma, with R0 is equal lambda times beta divided by A times D. So here we have illustrated that we have illustrated a function, a Lyapunov function, and we apply the E2 formulas, and we can get that the infection go to 0, and that's meaning that the persistence or the stochastic stability of the free equilibrium. So about the persistence here, if S equal D and C of lambda divided by D is positive, then for an initial value of in the set gamma, we have the persistence of mean of the population of the uninfected cells and the free virus and the immune system, with the function psi, capital Psi is given of X is given by the following expression, and the I is given. So we have an equivalence between Psi of lambda divided by D is positive to the parameter Rs is bigger than 1, and we can remark that if in the expression of R0 and Rs, if Rs is less than 1, automatically R0 is less than 1. And inversely, if RS is less, if R0 is less than 1, that's implied that RS less than 1, but inversely that RS less than 1 not imply that R0 is less than 1. We have tried in the numerical simulation this result, and that's meaning here we can remark that the persistence result is due to the RS is bigger than 1, and with the S is equal D, and that's the main of D and A is equal D. So that's the realized result in this part. So we have given a Lyapunov function, and we calculate this derivative by using the A2 formulas, and we can try that when R0, when RS is bigger than 1, we have the persistence case. So about the numerical simulation here, we can try the numerical simulation when R0 is equal 0.1 and RS is equal 0.04. So that's meaning the extinction of the infection, then of about the persistence and the deterministic viral load. But if R0 is equal 6.25 and RS is equal to 2 power 6, we can remark that we have the persistence of the infection, and we can prove the same result previously, but that the fluctuation of the solution is the solution have a fluctuation around the equilibriums or the endemic equilibriums. About the case of, we can give some important result here. If R0 is bigger than 1, we have the persistence of the deterministic, but here we have the RS is less than 1, we can get that we have the extinction of the infection. Is that's prove the crucial rule of the stochastic model compared with the deterministic model. And about the comparison, in the last part, we give some comparisons between the value of beta. If we change the value of beta, if we maximize the value of beta into 0.22, we can remarks or observe that we have maximize the number of the viral or the viral load. So this result is published in the Physical Statistical Mechanics and its application in the 2020, and we can prove the data of this paper in this is titled Stochastic Viral Infection Model with Lytic and Non-Lytic Immune Response driven by the living noise. So in the about some recommendation or some perspective of our works in possible scales to our investigation in this paper, one can extend the model proposed to various fractional order model, which are based upon several operators of fractional derivatives such as Dos, Known, the Louis Capito, and other fractional derivative. Also extend the model to an impulsive model such as that considered, and extend the model proposed to a spatio-temporal with Levy-Jump process. So other we can find other works. We have works we try. It's published in the 2020, 2021 in the Journal of Applied Mathematics and Computing. We have tried the stochastic predator prey problem by using the Levy-Jump model with the Crowley-Martin function And we have introduced the Stochastic. That's meaning we have introduced the effect of the maturation and pre-maturation of the prey and both the prey and predator in the model, and we try this result. It's very important and very nice result. We have gated in this paper. We can find this result in this paper. Also, we have more recently into 2023, we have published a paper in the collaboration with Zain Hussein and Delphine Torres of the University Aveiro, Portugal. Is a stochastic capital labor model with a logistic growth function. This paper is published such as a chapter of book in the dynamics control and optimization. Will be held in Aveiro. It's a meeting held in Aveiro into 2021 for the February, and selected and revised contribution is published such as a book of Springer. And more interesting result we have in collaboration of the University of Kurdistan, Iraq, with Hama Rasul and Rasul K.A. And the Professor Zaki Hamouche of the University Moulay Ismail and me. We have given a study into 2022. In this study, we have analyzed of a stochastic SVS model, epidemic model with the standard Brownian motion and the Levy jump. This result we have published in the journal Result in Physics. And more other result is a stochastic SECA epidemic model with Levy jump and Levy processes. Is a result we have published in several books that titled the Mathematical Analysis of Infectious Disease, and this result is a collaboration with the Zain and Torres of University of Aveiro, Portugal. And in this result, we have tried the stochastic and the program of, or the stochastic perturbation in a susceptible, infected, and chronic and asymptotic infection. And more recently, in the contribution on the numerical Ghana Day, so in the last years, we have published a model with stochastic capital labor Levy jump model with the precarious labor force. The precarious labor force is an important phenomenon that's represented the seasonality of the work, or the person in the training period. We have now qualification of the job. How can controlling these processes, if we have the seasonality of the job? For example, in Morocco, we can try the program or the reports of the activity of the years 2022. We have more seasonality works in the some region. For example, the region of Dar'at Filal, Marrakech SV, other regions, and we can compare by using the Levy jump process. We can get some motivate result and to controlling the dynamics of the capital labor. And in the last, we give some reference, some basic reference, but not the all reference, some basic reference in order to illustrate some paper here and some tools of the stochastic analysis in the journal. And thank you for your attention. If you have any question, any suggestion, any recommendation, and any perspective of this work, and will come